All right, so we're talking about now how we can get magnetic fields. Where do they come from? And we saw Biot-Savart, I'm not sure how to say it, but law gives us a method for defining infinitesimal field contributions and being able to make integrals to calculate it. And we're going to talk about Ampere's law soon, about another method similar to Gauss for electric fields, what we can use to get magnetic fields. But let's just kind of do a couple of examples here, not having to do integrals, just kind of taking averages and taking known equations to calculate fields. So we're going to say we have just a loop of wire, just one loop for now, and we have a voltage source here, some sort of voltage applied, and let's just so the first part is give current direction. So if the voltage source is oriented this way, the plus is up, minus is here, some sort of voltage source. And so the current then will come out of the plus, and depending on the resistance of the wire, right, we can get a certain current. But we're going to need a value for current here eventually, but let's just go ahead and draw a direction. So the current direction, of course, is going to go this way, and then this way. I guess I can draw eyes everywhere because this will help us with our right-hand rules. All right, so current just goes in one direction around a loop. Current is a flow, right? So the electrons are flowing, actually the opposite direction, but positive charge that effectively is flowing this way continuously. All right, so that's the I direction, and then we have to get our B. So now we don't have an external field. So in this case, we are going to have the current in the wire generating a field, right? So there's no external field. We won't draw a whole bunch of dots or X's on here. We're going to get the field from these flowing charges in the wire. And so we have our new right-hand rule where the thumb is the current, and then the field lines then are the fingers going around. And so in this wire, the field would be coming up from below and going around like this. If this were the wire, the field would be going around like this. So it's making big circles, right, around the pencil. Right? And so we could draw some loops like this. So this is the B field here. On this part, on this side, the current's going down, so then the B field is going around like this, and so coming up over the top, but also going down in the middle, right? And continuing on, the current is going to the left on the bottom, and so the field is making big circles around the wire. Fields are always making big circles around the wire, right? Or small, big circles around the wire, whatever size, right? So the B field is going like this. And then finally for this one, going around, current's up, current is a thumb, field is making circles this way. Right, so it's coming around like this on this side. All right, so we can kind of see all the different pieces of the wire are helping to make a field that goes down in the middle. It's all agreeing, right? It says field down in the middle, field up on the outside. So if we drew the field, we could draw it like this as well, coming out on the outside, up out of the page on the outside, going down in on the inside is what I've been trying to draw here. We could draw it like this as well, kind of things for the B field. Out on the outside, in on the inside, in all places. Okay, so just get used to looking at those notations and understanding which direction the things are. So making circles around the wire, all of the inside ones are going down, on the outside ones are coming up. Okay, so we got our B and I directions. Then it says, what is B at point P? So we got a point P here. We just kind of defined our X and Y axes where this is 0, 0, and we just said P is the point 1, 1. All right, so what is the field there? Well, we've got several different wires. B for a long straight wire is mu naught I over 2 pi r. And so are these long straight wires? Well, mostly. All right, so we're just going to go ahead and assume this is a long straight wire, so we don't have to do integrals around corners and figure out the details here. So we'll just make that assumption for now. So most of the times we're calculating fields in this class, we won't have to do integrals. We'll just be using some known ones and making maybe a few assumptions about uniformity of the field and things being long, kinds of assumptions. Okay, but we do have 4 different wires that will be contribute to the field. So I drew it like it's right here, and it's of course stronger here because you got dependence on 1 over r. They're going to have all the same current, right? The same current is flowing everywhere. So I is going to be the same everywhere. Mu naught is a constant. It's the same. 2 pi is constant. So r is the only thing that is different. And so we need to have a distance. And again, it's a little bit of an assumption, but we're just going to take the perpendicular distance to the wires as our r's, right? So these 2 wires that P is close to will have larger components of B, whereas these over here will have smaller components of B. Yeah, let's just go ahead with this example. I may want to add another example, but let's go with it. So B total then, I'm going to change and do a different C. So B total, just like with electric fields, we'll do superposition. So it's going to say, we'll maybe just call this side 1, side 2, side 3, side 4. So it's going to be B from wire 1 or side 1 plus B plus side 2 plus 3 plus the B from the 4th wire. Right? So we're just going to pretend like each wire individually is the only one there at first. Calculate its B using our long straight wire assumption, and then add them up. Or do we add them up? So that's the thing that I was wanting to do a vector problem. Well, this isn't very much of a vector problem, right? Because as we just saw, all the directions at this point, they are all the field components from every different wire is agreeing with each other and pointing down in, right? And so that's kind of boring in terms of direction. So if this is X and Y, we would say that the B's direction, if we wanted to get B as a vector, anyway, is going to be, B is going to be some magnitude, and its direction is negative Z direction. So it's going to be negative K hat, right? And of course, it'll be in Teslas. So all of these contribute in the same direction. If I had somehow made it 2 different sets of wires with some were going currents going the opposite direction, we could have gotten some that added up and some that cancel was some positive, some negative, so they would cancel. But in this case, it's a little too easy, but we'll go with it. So we've got for B1, it's going to be mu naught I1 over 2 pi R1, so forth. Mu naught I2, 2 pi R2. Mu naught I3, 2 pi R3. All right, that's a 3. And the I's are all the same because it's all the same wire just bending around the corners. And so we can do some factoring here. So we got mu naught I over 2 pi times 1 over R1, which is R1 is the distance to wire 1. Wire 1 is here. So the distance, we said this whole thing was 6, and this is at 1, 1, so this difference is 5, so 0.05 meters. All right, so this is R1, 6 centimeters minus 1 centimeter. All right, this is R1. And then we have plus 1 over R2 because everything else factors out. So R2 is here. Same kind of argument. This whole thing is 8. We've got 1, so the distance from this point to this wire, which is R2, is going to be 7 centimeters, 0.07 meters. And then these two are just both 1 centimeter away. All right, so turning on new calculator. There we go. Well, so what is mu naught? Mu naught is 4 pi 10 to the negative 7. And I, we need an I. Let's say I equals 2 amps. I have to have a number, all right? 2 amps. Okay, so we've got the pi's will cancel, and the 2 will cancel, make a, with the 4 and make it 2. All right, so we've got 2 times 10 to the negative 7 divided by, oh, we got no divided by, everything canceled out. Take out the divided by. Multiplied by this whole big thing, 1 divided by 0.05 plus 1 divided by 0.07 plus 1 divided by 0.01 plus 1 divided by 0.01. Did it interpret everything right? Yes, but I forgot something. I forgot this 2 amps over here, so let's get that back and put another 2 in there. Let's change that to a 4. 2 times 2, yes. All right, so we've got 93.7 microteslas for the magnitude. So B total as a vector is negative 93.7 k hat microteslas. Taking Z is out of the page. Okay, how can we do one that, or I want to look at one that is a vector problem. So for C, let's just say we have a wire here, a wire here, and let's just put another wire here. Let's say we have 2 amps coming out of the page, 2 amps going in the page, 3 amps going into the page here, some sort of XY coordinate system. And let's say this is, I don't know, it looks about like 4 centimeters, and let's call this 3 centimeters. And let's say we want, B at 1, 1 again, is what? So how would we do this one? It's a little lot trickier. Let's see, maybe I picked a hard one, but let's at least set it up. So we're going to have B total is still B1 plus B2 plus B3. But now the directions are different. So let's go ahead and get the directions. So these are wires, like trying to draw wires coming out of the page. So this is a long straight wire going into the page, right? Trying to do 3D effect here. And so what direction is the field for a wire, for this 2 amp wire? The current is flowing out. So we get the direction, we put our thumb in the direction going out. And so the field is going around like this, making circles around. And so at this point, we don't really care. I mean, it's making circles like this all around, right? But we really care about this point right here. We're asking about this B that we call B at 1, 1. So I guess let's just call this wire 1, wire 2, wire 3. And so B1 then would look something like that, right? Because it's current's coming out, field going around, making circles. It's going to be tangent to the circle. Try to draw a tangent to the circle. Anyway, this should be a right angle right here, right? Draw a radius to the point, draw a right angle, and that's the B, right? Just touching the surface of that circle. That's B1. How about B2? What would the field look like from here? Because we're going to add the field as vectors. So this one, current's going down in, right? It's a long wire parallel to this guy, but now it's going, this one's fields are circles around it. And so if we can just do the radius and perpendicular thing here, this one, yeah, it's going in. So this maybe they're the same size. This one is should be closer, although it doesn't necessarily look like it, so this one should be a bit longer, right, maybe? Getting messy here, but this would be B2. Okay? And then finally, let's look at this guy. This third one, it's going down in, so its field is a circle like that, making circles around like this, like the fingers, and so it's making circles this way, or its B field. So when it gets here, draw a radius, draw 90 degrees, maybe something like that. So this one would be B3. Trying to make that be perpendicular there. All right, so what is B total? We got to add all these guys up. So maybe we can make a parallelogram with these, so it gets to here, and then that one adds on to the end of those two. So maybe something like that, translating this over here. So B total is something like that. Just kind of graphically trying to add the three vectors. Hopefully you can see. I should have made some colors on here. So B total is just taking these, putting them all tip to tip, tip to tail. Yeah, say B2, B1, B3, adding them all up. Tip, tail to tip, tail to tip. And then that starting point, ending point should be the same as B total. Okay, so how can we get these? Well, we'd have to find the individual vectors, and it's kind of a pain. I should have picked something easier to deal with, but let's just kind of start off with, let's just try this one here. Let's do, did I call that one B1? So let's get B1. All right, so we got to get it as x and y components, or magnitude and angle. We've got that, we get a triangle in here somewhere. So this whole distance was 3, so this piece, and this was at 1, 1, so this side should be 2 centimeters, whereas this was 1, 1, this was at the x and y axis, anyway, on the y axis. So this should be 1, so there's a little triangle in there. That's 1 and 2, 90 degrees. This direction is R, and so for R1, and so B is perpendicular to that, like this. B1. Okay, so if we find, say we can get this angle from just the way from the physical setup. If we get that for theta, how does that relate to this guy? Let's continue on here. So if theta is there, let's see. So theta is here, and so this might be something we call alpha. This is 90 degrees, and so this was alpha. This is also alpha. So alpha and plus theta make 90 in this triangle, so that the whole triangle is 180. So this alpha plus theta make 90, yes, okay. And so this is a 90 here also, and so this must be theta. Whew, okay, so the angle then for this vector B1, its angle with respect to horizontal is this theta, right? What is theta? Maybe we should call it theta 1. So theta 1, well, if we just look at the triangle, we can say tangent theta 1 is what? Tangent theta 1 is opposite over adjacent, so it's 1/2. So theta 1 is inverse tangent of 1/2. I don't know if you can see that, but anyway, inverse tangent of 0.5. I can barely see it. 26.6 degrees. And so, oh, running out of room. So we could calculate the magnitude of B1 then as using this formula up here like we did before. Mu naught I is 2 mu naught I1 over 2 pi, and then R1, what is R1? We'd have to get the hypotenuse of this triangle. Right? Did I do that right? It was only 3. Okay. So the hypotenuse of the triangle is R1. Lengthwise, R1 is the square root of 2 squared plus 1 squared, right? Just by Pythagorean theorem. All right, and so, yeah, we just want R in the bottom, so we want square root of 0.02 squared, actually, plus 0.01 squared. All right, so we can calculate the magnitude of B, and we have the angle of B for B1, for example. So then B1 is going to be, I guess let's go ahead and calculate it. So we got 4e negative 7 times pi, that's mu naught, times I1, which is 2, divided by, I could have canceled stuff, but anyway, 2 times pi times square root of 0.02 squared plus 0.01 squared. What is going on here? And it's mad at me about syntax error. Okay. 4 pi times 10 to the negative, 4 pi 10 to the negative 7 times 2 divided by 2 times pi times square root 0.01 squared plus 0.02 squared. Okay, so we get 17.9 microteslas. But then what is that at an angle of 26.6 degrees, right? And so to get it in terms of x and y parts, we're going to do x, actually both of them are positive, just checking on B1, both of them are positive, so it's going to be 17.9 cosine 26.6 I hat plus 17.9 sine 26.6 j hat, right? Looking at these other ones, B3 would also be positive if we did the same process. B2 would have a negative I hat, or negative j hat, but a positive I hat. All right, so 17.9 cosine 26.6. So it would be 16 I hat plus 17.9 sine 26.6. 8. Yeah, pretty much. Okay. Double. Yeah. Okay. Anyway, j hat. And this is microteslas. Is B1. Okay, I want to get to the next one. So for this, and I'm running out of room, but if we wanted to do a complete problem like this, we would get B1, that's a vector. Do the same process for B2, figure out its angle to the horizontal, so you can convert it, make it into a vector with I and j components, I hat, j hat components, get all the pieces, and then add them up. All right. Let's continue on with this other example here, just to see a different shape. So now we have what is called a solenoid. It's just and in this case, we're just treating it as an air-filled solenoid, which isn't really a great way to make something that you want to have strong magnetic fields in. You would put an iron core or something that's a magnetic material in there, but for now we're just doing air-filled. So for a solenoid, it's just a coil wrapped around something that's not magnetic, right? And so what are the field lines for a solenoid? So we have another, or we can do a couple different right-hand rules, but if we have a current going this way, and so the wire goes around, so it's going, the currents are all going up on the front, right, goes down the back, up on the front, so we have a whole bunch of currents going up, something along those lines, like that. And so if we draw the fields for each thing, use a right-hand rule for each one, the circles going around the current, going around each one, we would draw these little circles. But at least that gives us an idea of the field would be going to the left on the inside on that right, and to the right on the outside. Most of the time when we're worrying about these solenoids, we would just draw the field on the inside, and so the field would be going like this. So we have our B field on the inside going that direction. If we draw our field lines, we would have field lines that go, anyway, making a mess, but go out and around, and so they're concentrated here, and they continue. Magnetic field lines are continuous, so they would go through the inside and then continue on around. All right, so the B field lines would be something like this. Okay. All right, and so what a mess we got going on here. So that's the B field lines. B on the outside, on the long side, so B along here is basically 0. We'll usually assume B is 0 on the solenoids here because the field lines are going out and coming around, and so right next to this, there may be some effect, but the things cancel out from all of these little wires, and so the main field effect is around the outside. All right, let's go ahead and calculate B on the inside. And so we have a formula. I think one of the videos we derived the formula for that. Don't remember. We'll do it with Ampere's law in a different example here soon. But B on the inside is mu naught. Which version do we want to do? Let's just do mu naught Ni. Okay, where little n is the number of turns, number of loops or coils, however we want to think of it. We usually call them turns per length. Turns per meter, kind of a unit, right? Which would be, if we have the whole thing and we know the whole length, we would just take the total number of turns, usually call that capital N, and divide by the total length, capital L. So if we have some length L and some number of turns N here, it would be little n. And so for this example then, we'd have to, I didn't give a current. Anyway, we would need to know either the length of the coil and the number of turns, or the number of turns per unit length. You say measure a piece of it, count, if you have a great big coil with tons of wraps on it, but maybe you can count a little, 2 centimeter section, and then divide that by the 2 centimeters, so you can get the N number. But basically, once we have a current, again, we'll just say I equals 2 amps again, for example. And so then B inside is just 4 pi times 10 to the negative 7 times N. Oh, we would have to have all these numbers. Well, let's say we have 200 turns. We wrap 200 wraps around this thing, and let's say that the length is 8 centimeters. All right, so we'll do 200 over 0.08 meters, and then 2 amps. So we would have B on the inside of the solenoid for E negative 7 times pi times 200 times 2 divided by 0.08. Looks good. So 6.28 mil, is it negative 3? Yeah, milliteslas for our field inside the solenoid. Okay, so again, or maybe I didn't even talk about it. So another right-hand rule. So we did the little right-hand rule. We could take each current and get the field like this, or we can think of making our fingers be the coil, the wraps of the coil, and then your thumb will point in the direction of the magnetic field also. So yet another right-hand rule, maybe third, if you're counting the two forces as one. You can think of grabbing a solenoid or a toroid, whatever you have that has a whole bunch of wraps on it, and then your thumb, with your fingers being the current direction, current going that way around the coil. Feel this that way. Okay, let's go ahead and stop there.